Hi, everyone. Today we're going to we're starting our unit on energy. Energy is one of the coolest things in all of physics. Why? First of all, it's not a vector quantity, which makes it a lot easier to work with. And second of all, it's something that's conserved. That is, the total amount of energy in the universe is always constant. And it was James Prescott Joule who first realized this, that you can't destroy energy. All you can do is convert it into another form. Typically, that final form is always in the form of heat. All energy, light, sound, eventually gets absorbed by materials and gets converted into just the thermal vibrations or heat energy of that system. But he was the one who realized that, hey, it's all the same. Let's take a quick look at this, and I'll give you the mathematical definition of work. Warning, the mathematical definition of work is slightly different than the one that you're familiar with, especially when you think about homework. So, as I said, it's different from the common use of the word. In physics, work involves both force and distance. Mathematically, work is equal to force times your change in position, delta x, times the cosine of the angle between those two vector quantities. And work can be either positive or negative, depending on the value of that cosine. If you remember again, cosine is 1 if theta is 0. If theta is 90 degrees, then cosine of 90 degrees is 0, and cosine of 180 degrees is negative 1. And of course, you can get all ranges in between that. So for example, if you've got a force in one direction and your displacement, delta x, is in the same direction, the angle between these two would be 0, and you have positive work. On the other hand, if your force is this way and your displacement's the opposite direction, then you're dealing with cosine of 180 degrees, and your work is going to be negative. Work adds or removes energy from a system. If you have positive work, you're adding energy to that system. If you have negative work, if you're removing it from that system. Now, you might say, wait a second, didn't you just say energy is always conserved? You're absolutely right. When we remove energy from one system, we add it to another. Or if we add energy to the system, it means we're borrowing it from another system to bring it there. The total amount of energy in the universe is conserved, but we can move it around by using work to transfer energy from one system to another. So it's kind of fun that way. So some quick examples here. If you're pushing a car, you're doing positive work. The red vector here represents your force that you're exerting, the green vector, the displacement, and in this case, the angle between those is 0, so we have positive work. You're adding energy to the car. In this case, this boy is catching a baseball. Baseball's coming down this way, catching the glove. The force he's exerting to stop the baseball is in this direction, the red vector. Meanwhile, his glove is moving backwards, downward as he's doing this. And so the angle between these two is 180 degrees. And so when you do the cosine of 180 degrees, you get a negative result. The boy's doing negative work on the baseball, which means the baseball is actually losing energy, which is kind of an unusual idea. All right. The units for work are newtons times meters. Because it's used so frequently in physics, like I said, it's one of the more cooler things. The units for work are not just given Newton meters, it's given its own special unit called the joule, abbreviated just capital J. Now, just some quick examples on this one. You could push as hard as you wanted to against the wall, but you would never do any work because there's no delta x, there's no displacement as you're pushing on the wall. Now, some of you are saying, well, Mr. Calmer, technically, didn't you say walls are springs? Everything's a spring, so it moved a little bit? Yeah. So you probably did a little bit of work, but basically close to 0. And displacement without a force does not do work. Again, think about an asteroid just coasting through space. It has a displacement, but there's no force acting on it. Remember, there's no force required to keep an object moving at constant velocity. And then finally, this is the toughest one and the hardest one for people to get their brains wrapped around. Force that's perpendicular to displacement does not do work. For example, the normal force on a car as the car is moving horizontally, it does not do work on the car. It does not add energy to the system, it doesn't add energy to the car. It doesn't remove energy from the car. It's doing no work. So for example, when you're carrying your books down the hallway, as long as you're not lifting them or lowering them, believe it or not, the force you're exerting upward, that normal force, and the displacement, the opposite direction, or perpendicular to it, does no work. You're like, what? No, it's hard to carry my books down the hallway. Yeah, but you can actually replace yourself with a frictionless cart, And that cart could also move your books down the hallway at a constant speed, and you'd be doing no work, or it would be doing no work as well. Work is very specific in physics. So how much work does normal force do in a sliding block of dry ice? Dry ice is solid carbon dioxide. If you put a block on a tabletop, the part where it touches the table evaporates and it floats. So it's almost frictionless. So how much does the normal force do on this block of floating dry ice? The answer, of course, is 0. Dry ice is moving one way. The normal force is acting perpendicular to the surface. 0 work is done. How much work is the force of gravity doing on the table in front of you? There's a force, but because there's no displacement on the table, again, the work is 0. And then this one I want you to think about for a brief moment. How much work is the sun doing on the Earth? The Earth is almost in a perfectly circular orbit around the sun. Here's the sun, really badly drawn. Here's the Earth moving in orbit. And again, remember, most of you know that what's keeping the Earth in orbit is the force of gravity that the sun is exerting on the Earth. Take a quick moment, think about it, talk with your neighbor. How much work, if you've got one, how much work does that force do? And I'll give you 5 seconds. Just pause the video if you need more. If you'd answered 0, you're absolutely correct. And you're like, what? Yeah, the force is this way, and at every single instant in time, the velocity of the planet, or its displacement, which is along the velocity vector, is perpendicular to the force. So at every single instant, the force of gravity does no work because the planet's moving this way while the force of gravity is going straight down that, or straight towards the sun. And at every single point, it's perpendicular. Trick question, I know, but still fun to look at. Here's another quick question. If you lower a 1 kilogram mass 1 meter down at a constant velocity, how much work does the gravitational force do on the mass? Well, again, if you just draw the gravitational force, it's that way. And you can probably very quickly realize, okay, it's going to be the force, 9.8 newtons, times the 1 meter, times the cosine of the angle between it, which in this case is 0 degrees. Cosine of 0 degrees, 1. And then, oh, sorry, there it is. And so the work done by gravity would be positive 9.8 joules. Just plugging in the numbers. But then I can ask you the question is, how much work is being done by your hand? Well, if you're lowering this at constant velocity, means the net force on the mass is 0, means you must be exerting a force of 9.8 newtons upward as you lower the mass. So there's no net force on the mass. So how much work is done by your hand? Well, this time the force of your hand's upward, displacement's downward. And if you do the math, the work done by your hand is negative 9.8. And at this point, you might say, wait a second, hold it. So if gravity's doing positive work and my hand's doing negative work, then wait a second, the total energy gained by the mass is 0? You got it. We're going to talk about kinetic energy a little bit later. What's happening here? The kinetic energy of the mass is staying constant. Why? No energy is being added or removed. Gravity is doing positive work on it while your hand's doing negative work. And so the net work done on it is 0. No energy gain or loss. Moving forward. Oh, sorry, jumped the gun that one. Take a look at this one. We looked at this example before, but here's a math one. If you exerted 500 newtons for a distance of 10 meters to get the stall card going, how much work did you do? In this case, the force and the displacement are in the same direction, and so you're going to do positive 500 joules. And now that slightly trickier question, how much energy does the car gain or lose, ignoring any losses due to friction? Well, remember, work is a special quantity. It adds or removes energy from the system. If you do positive 5,000 joules of work on the car, the energy change of the car, it's going to gain 5,000 joules. It really is that simple. A couple more examples here. If a child's riding a bike, is rolling towards you, and you apply a force of 200 newtons as you move backwards 5 meters, so you're slowing her down, how much work do you do? Plugging in the numbers there real quick, 200 newtons times 5 meters times the cosine of 180 degrees, because you're exerting a force one way as you're moving backwards the other way, you'll get negative 1,000 joules. And how much energy does the biker and rider gain or lose, ignoring any energy lost due to friction? Again, the work is equal to the change in energy of the system, so the bicyclist or the bike and the bike rider are going to lose 1,000 joules of energy. Kind of feeling the pattern to this one? Good. So at this point, I'm going to take a break from this one, and I'll take a look at the first one here. You've got a couple of textbook problems that I'd like you to try real quick. The solutions are linked on the Canvas page. You've got 6 textbook, or a total of 7 textbook problems, 6 from Survey, 1 from OpenStax. And I'd like you to give these a try. They're dealing with the work equation, and please pause the video, take a break from this, try these, check your solutions to make sure you understand what's working, and ask me any questions as you go along. Good luck with this one. We'll see you in just a little bit.